Okay, lesson 4, reflection from curved mirrors. So spherical mirror. So a spherical mirror is a portion of a sphere that has been polished on one side to make a reflecting surface. There's two types of spherical mirrors, concave and convex. So let's start with concave. This is where the inside of the sphere is the mirror surface. So here I have a concave mirror. There's two sides, has the back side, which is not a mirror, and the front side, which is. I've tried to show that on here by drawing one side of the mirror as gray. That's supposed to be the shiny side. And if it's a concave mirror, so if we pretend that this pen is the person's going to stand in front of the mirror, which means the person's going to stand on the same side as the shiny side. And the mirror is going to bulge away from the person. So I don't know if you can really see that very easily, but the mirror is bulging out like this. So that's concave. And then convex is the opposite. So again, we're going to put our person on the same side as the shiny stuff. And this time though, the mirror is bulging towards the pen or the person. And so the mirror is bulging this way. So in this lesson, we're going to be talking a lot about object versus image. I'll just show you what that means. So say I have my concave mirror here again, and I'm going to hold my pencil in front of the mirror. So the actual pencil here, this is the object. The pen that you see in the mirror, that is the image. Okay, and then we're going to be talking about real versus virtual images. I don't want you to get too hung up on real versus virtual. For right now, you can just remember that anytime we have an upside down or an inverted image, that's a real image. Anytime we have a right side up image, then that's going to be virtual. Okay, so mirrors can form two types of images, real images and virtual images. It's always going to be one or the other. We're going to begin by looking at virtual images. There's also one more type of mirror that we don't look at too much in Physics 30, but it's called a plane or a flat mirror. So this is a flat mirror. As you can see, it has no curvature to it at all. These types of mirrors form virtual images. So in your bathroom, you probably have a plane mirror, and when you look at yourself in that mirror, you don't look upside down, right? You look right side up. And anything that's right side up is a virtual image. So plane mirrors always form virtual images. Now, we can have a look at this diagram here to sort of try to explain how a virtual image forms. So imagine that this object lights up. Okay, so the object is giving off light. One light ray is going to come from the corner of the object towards the mirror. That's called the incident light ray. And when that ray hits the mirror, it's going to bounce off the mirror. It's going to reflect off, so this is called the reflected ray, and it's going to go into your eye. And then we can do this again for the other corner of the object. So this is another incident ray. And then this one here is going to bounce off the mirror. It's going to reflect, and that's also going to be considered a reflected ray. Okay, now we're going to try to explain what you actually see in the mirror. So what we're going to do is we're going to trace the reflected rays back. So this corner right here, we'll call this corner A. So see how this went, and then I traced it back to here. This is where corner A is going to appear in the mirror. And then this one, we'll call this corner B. So this light ray went, and then we trace this reflected ray back. So this is where corner B is going to appear in the mirror. So we're going to have something like this, and then this is where our image would be. The idea here, okay, is that the image forms behind the mirror. So here's our mirror. This side of the mirror is the front side. The front side is always the side that the person stands on. Or in other words, the front side is always the shiny side of the mirror. The back side of the mirror is behind the mirror. That's the darker side, the non-shiny side of the mirror. Okay, so notice here the image is located behind the mirror, and these reflected rays don't ever actually go behind the mirror. Okay, mirrors are opaque. They don't let light rays pass through them. The light rays hit them and bounce off. But we can trace the reflected rays back for ourselves to find out where it looks like the image would be. And so even though the light rays don't actually go behind the mirror, it still looks to us like the image is there. And we're not going to worry too much about that because that's getting into some biology stuff actually. But anyway, that's why it says here the light rays appear to be behind the mirror. They're not actually there. The orientation is going to be upright, so meaning not upside down. And can the image be projected on a screen? No, and we'll talk about that more later. For right now, don't worry about it. Okay, it turns out what makes this image here virtual is the fact that we traced the reflected rays back. Okay, you'll see that when we have a real image, we actually don't have to do any ray tracing. And that probably doesn't make sense yet, but it will in a little bit when we start to look at ray diagrams. Okay, so whenever we talk about images in this class, we can talk about 3 features that the image has. So we can talk about the image size. So is the image bigger or smaller than the object itself? So for example, if I do this again, do you notice how if I hold the pen here, the pen itself is smaller and the image is bigger? Okay, so we can always talk about the size of the image relative to the size of the original object. We can talk about the orientation. So is the image upright or inverted? And then we can talk about the type. Is it real or is it virtual? For plane mirrors, which is what we were just looking at, you're just going to want to memorize the size is always identical to the object. So if I hold this plane mirror here and then I hold the pen in front of it, the pen and the object are always the same size. Okay, one doesn't look bigger than the other. That means we have a magnification of 1. So a magnification of 1 just means the image is 1 times the size of the object, or in other words, they're the same size. The orientation is upright, right? Pen doesn't look upside down in the mirror, and it's virtual, and the reason we know it's virtual is things that are upright are always virtual. All right, so spherical mirror vocabulary. So I want you to imagine here you have a mirror, and this could be concave or convex. So either the shiny side of the mirror could be here if it's concave, or it could be here if it's convex. It doesn't really matter. The vocabulary is going to be the same either way. So if you imagine that this mirror takes up a whole sphere, in the very middle of that sphere, we have what's called the center of curvature. Right here, we have the vertex. So C is center of curvature, and V is vertex, okay? If we draw a line through the middle of the sphere, that's what's called the principal axis. Okay, so the vertex is where the principal axis meets the mirror surface. And then halfway between the center of curvature and the vertex, we have what's called the focal point of the mirror. If we measure from the center of curvature to the vertex, that's going to be what we call R. So just a second here, F is the focal point. Okay, R is the radius of curvature. And if we measure from F to V, then that's what's called the focal length. So this right here is the focal length. And something to know, okay, is that your focal length is always going to be half your radius of curvature. Okay, so I just want to show you what happens here when we have a concave mirror. These are the 5 cases. So if I hold the pen really close to the mirror, this is case 5, notice that the image of the pen is upright and it looks bigger than the pen itself. And then if I kind of move the pen further away, at a certain point, that image disappears. It's like right there, there's no image forming. That's case 4. Moving the pen up a little bit more. Okay, about right here, now this pen is upside down. So now we have a real image, and the image right now looks a little bit bigger than the pen itself, so that's case 3. Continuing to move up, somewhere in here, the image and the object are the same size, so that's case 2. And then if I move up even further, now we're in case 1 where the image is smaller, inverted, and real. All right, so we're gonna skip this part here that says drawing ray diagrams because you know that already from watching the ray diagram video, but we're gonna have a look at this diagram here. So here we've got a ray diagram. I've drawn in the image there. So remember, the image is drawn at the point where the reflected rays, which are drawn as dotted lines, all cross. And I want to talk about why this is a real image. So basically, when you're drawing a ray diagram, if you have to trace the reflected rays back before you can draw the image, that's what makes it a virtual image. In this case, we didn't have to trace any rays back. And so that's what makes this a real image, okay? So the image on the ray diagram here is a real image because light rays actually pass through this point where the image goes. There's no tracing back involved. So whenever we have a real images always form in front of the mirror, which is the shiny side of the mirror. They're always inverted. And can they be projected on a screen? Yes, they can. That's because if you took a screen and you put a screen right here, okay, the screen could just be a piece of paper or an index card or something. If you actually looked on that index card, you would see an image forming on it. In the case of a virtual one, if let's say your image forms back here. So let's say you trace your rays back and your image is, somewhere over here. If you try to put a screen at that location, no light is actually going to ever reach it. And so, because the light doesn't actually ever go through the mirror, right? The light just hits the mirror and then bounces off. The light doesn't get back here. So you wouldn't see anything on the screen. So that's why real images can be projected on a screen, whereas virtual images cannot be. Okay, so this part here just summarizes what you saw in the video about ray diagrams, and you can fill in the acronym for each case. And then for this part, we're gonna actually look at this sheet of paper that I printed a little bit bigger just to make it easier to see. I'm gonna suggest that you pause the video, fill in all of this, and then come back. Okay, so here, these are sign conventions that you just have to memorize. There's no real reasoning behind them that we're gonna talk about, you just have to know them. And the reason you have to know them is so that you can actually do the examples that we're gonna do in a second. So just something to be careful of is right here specifically. Remember that a concave mirror can make either a real image or a virtual image depending on where the object is placed. So don't fall into the trap of saying that for concave mirrors, DI is always positive and for convex it's always negative. That's not true. So that's why I've written here, DI doesn't depend on the mirror type. Instead, it depends on the object type. So real images always have positive DI, virtual images always have negative DI. All right, so mirror examples. So these are our mirror equations that use the symbols that we introduced in the last page. So let's jump into example 1 and see how to do it. So a 5 centimeter tall object, so that's HO. HO is always positive, is placed 60 centimeters away from a spherical mirror. So that's DO, which is also always positive, with an 80 centimeter radius of curvature. Now the radius of curvature can be positive or negative depending on the mirror type. So for right now, I'm just gonna write plus or minus 80. And then it says describe the image formed if the mirror is concave. So we need to have memorized that for a concave mirror, the radius of curvature is positive. So this is gonna be positive 80. And we never really use the radius of curvature in our math. So we're gonna turn this into a focal length. And we see that right here, that the focal length is half of the radius of curvature. So the focal length here is gonna be 40, and it'll be positive 40 because for concave mirror, the focal length is positive always. Okay, we're gonna describe the image formed. I'm gonna show you how to do that mathematically. So we're gonna use this middle formula to actually calculate DI. So we have 1 over F equals 1 over DO plus 1 over DI. And let's rearrange for DI by subtracting 1 over DO from both sides. So 1 over F minus 1 over DO, that's equal to 1 over DI. So 1 over f, it's going to be 1 over 40 centimeters, minus 1 over do, so 1 over 60 centimeters. That's going to be equal to 1 over di. Now I just want to show you, when I put this in my calculator, say I have 1 over 5. That's the same thing as doing 5 to the power of -1. So how you type it in your calculator is up to you, but I'm going to use the -1 button because it's just a little bit easier. So when I type this in, I'm going to type in 40 to the power of -1 minus 60 to the power of -1, and that number there is 1 over di. So 1 over di is 0.0083 repeat. Okay, and the units for that are centimeters to the power of -1, or if you prefer, you can write 1 over centimeters. Same thing. Okay, and that's because over here, this isn't just centimeters, this is 1 over centimeters. Okay, so we know what 1 over di is. Now we want to get just plain old di. To do that, we're going to do 1 over di. Okay, and so this is going to be 1 over 0.0083 repeat centimeters inverse. So in my calculator, I'm just going to do 1 over the answer, and that gives me 120. Okay, so 120 is di. Now, we are asked to describe the image formed, so we need to think about what this di value actually tells us. Because this di value is positive, and we know that positive di values always go with real images, that means that our image is real. Okay, so positive di, real image. We also know that real images are always inverted. So I can also write here, image is inverted. Okay, now I need to also tell about the size. So whenever it says describe the image, that means talk about those 3 attributes that images can have. So talk about the size, talk about the orientation, and talk about the type. So this here is the type, this one here is the orientation. Now I want to be able to talk about the size. And to do that, we're going to look at the magnification. Okay, to calculate magnification, you can either use HI and HO, or you can use DI and DO. I'm going to use DI and DO here just because I have both of those numbers already. I don't have HI, so I'm not going to use that. So M is negative DI over DO. So let's go ahead and let's calculate M. So negative DI, so negative, and then DI was 120 centimeters. And then DO was 60. So that should just be -2. And so let's think about what this tells us about the object. So magnification always has 2 parts. It has a sign, so in this case it's negative, and it also has the number. The sign actually tells you whether the object is upright or inverted. So a negative magnification is going to be inverted, okay, which we actually already knew. But I'm just pointing it out because you want to make sure that your answers are consistent, because if you're getting a positive number here for magnification, then you know you did something wrong. So anyway, inverted, and then there's the number part, okay? And if the magnification is bigger than 1, which 2 is, then that means your image is bigger than your object. Okay, so we're in the bigger, inverted, and real case. And we can verify our answer using those ray diagram acronyms that we have memorized. So we just draw a quick picture here. So if we have a concave mirror, here's the mirror, here's the principal axis. Okay, the radius of curvature and the focal length are going to be here. So radius of curvature is 60. Focal length is 40. Oh no, sorry. Radius of curvature is 80 and the focal length is 40. Okay, and our object is placed at 60 centimeters. So 60 centimeters is somewhere between 40 and 80, like right here. So this arrow is our object, okay? And we know, so for going back to this page for a minute, that means we're in case 3. Our object is between C and F, so we would expect the image to be bigger, inverted, and real, which it is. So we can use that to check our answer. Okay. Okay. Example 1, part B says the mirror is convex. So same example, but just now the mirror is convex. So we're gonna do the exact same thing here. So starting with this, we know from what we did a minute ago, okay, that 1 over di is equal to 1 over f minus 1 over do. However, this time, remember to make the focal length negative. So the focal length in part A was positive 40. So here in part B, it's going to be negative 40. Okay, and the question's not going to tell you to make it negative. You have to remember to do that when you see that it's a convex mirror. So here we're going to have 1 over negative 40 centimeters minus 1 over 60 centimeters. Okay, so negative 40 to the power of negative 1 minus 60 to the power of negative 1, and that gives negative 0.0416. Repeat. Units are centimeters inverse. di is going to be 1 over the number that we just got, so negative 24 centimeters. Okay, because we got a negative di value, that tells us that we have a virtual image. Okay, and we know that virtual things are always upright. Okay, and then now we're going to calculate the magnification again so that we can talk about the size. So magnification is negative di over do. So negative times negative 24 over do, which is 60. So negative times negative 24 over 60 is positive 0.4. Okay, so again, the magnification has 2 parts. We see that this is a positive magnification. Positive magnification means an upright image. So that's good, that's consistent with what we got earlier. And now we look at the number part. So this number is less than 1. So this means that we are going to have an image that's smaller than the original object. So we're in the SUV case, which makes sense because if we look here, whenever we have a convex mirror, there's only one possibility. It always has to be SUV. Okay, and I will just mention, the original question gave us the height of the object. I didn't use that anywhere in my math, so sometimes they'll give you extra information that you don't necessarily need. Okay, example 2. The upright image of an object is 1/3 the size of the object. Okay, they're trying to tell us about the magnification there. So the magnification, because the image is upright, it's positive. You don't actually have to write the plus sign there, but I'll do it just to be clear. And because the image is 1/3 the size of the object, that means the magnification is positive 1/3. The object is 20 centimeters from the mirror. So DO is 20, always positive. It says, what type of mirror is it, and what is its focal length? Okay, so we're going to try to find the focal length here. To do that, we're going to use 1 over f equals 1 over do plus 1 over di. That's the only formula that has focal length in it, so I have to use that. Okay, so to do this, I'm going to need to know what di is. So let's use our magnification formula. Just do it over here. So magnification is negative di over do. So m do equals negative di. So that means negative m do equals di. Okay, so negative m, so negative times 1/3 times do gives negative 6.6 repeat centimeters as our di value. Okay, so now we can go over here and we can put our numbers in. So 1 over f is going to be 1 over do, so 1 over 20, plus 1 over di, so 1 over negative 6.6. Okay, putting that in the calculator, so 20 inverse plus this number that I just got, inverse, and that gives negative 0.10 centimeters inverse. Okay, this is 1 over f right now. So to get f, we have to do 1 over f. So that's just 1 over the number that I just got. And that gives negative 10 centimeters. Okay, so we found our focal length. The focal length is negative 10. And now it says, what type of mirror is it? So we have memorized that focal lengths are always negative when you have a convex mirror. So because we got a negative here, the type of mirror must have been convex. All right, example 3. So a student looks in a magnifying mirror and notices that her image appears upright and 3 times larger than usual. So that means the magnification is +3, positive because it's upright. And then it says the mirror has a focal length of 10 centimeters. How far from the mirror was the student standing? Okay, so we're looking for DO. That's going to be how far the student was from the mirror. And remember, we have to think about whether that focal length is positive or negative. So if we have our 5 cases here, okay, notice how here it says that the image is upright and it's also larger. So the only time that we end up with an upright image is these 2 cases right here, concave case 5 or convex. But in the case of concave, we get a larger image. In the case of convex, we get a smaller one. So we know that we have to be in this case right here. So this is a concave mirror. And for a concave mirror, the focal length is always positive. So we can write here that the focal length is +10. Okay, so to find DO, I'm eventually going to want to use this formula right here. 1 over f equals 1 over DO plus 1 over DI. Okay, and just so it's done, I'm going to rearrange that for DO right now. So 1 over f minus 1 over DI equals 1 over DO. Okay, now I know what f is, okay, it's in my list, but I don't know what DI is. So I'm actually missing 2 things here. I'm missing both DO and DI. So what I'll do is I'll try to use this magnification. So we'll write down here magnification is negative DI over DO. Now we know that the magnification is 3, so we can write 3 equals negative DI over DO, but we're still missing 2 things. We still don't know DI or DO. So when that happens, you have to set up a system of equations, which means you have to plug one equation into the other. So what I'm going to do here is where I see DI, I'm going to go ahead and plug in DI from down here. So this is what I mean by this. So let's rearrange. So 3 times DO is equal to negative DI. So I will just show you a shortcut you can take when you get to this step. If you want to use your calculator to solve instead of finding a common denominator manually, you can. So what you do is you just ignore the DO there. So this is really like 1 over, ignoring DO, just put a 1 on the bottom, plus 1 over negative 3. So in my calculator, 1 over 1 plus 1 over negative 3. And that gives me a decimal. I can turn that back into a fraction by hitting the math button and then selecting fraction. And that gives me 2/3. But then now I have to put the DO back in there. So DO is on the bottom of the fraction. So there, which is exactly what I got here when I did it by hand. And then the rest of the solution would be the same as what I just did.